Hi, in this video I am discussing the topics related to force in A-level syllabus. Edexcel, Cambridge, International Baccalaureate all have almost the same topics in force. Only the difference, Edexcel, they don't use F equal mu R. That means the friction related to coefficient of friction, that equation is not there in Edexcel. But all the subjects they have. But whatever it is, so this video is common for all the A-level syllabuses. Also, you can directly link to the subtopic by seeing the description of this video. In the description of this video, I put the timestamp. So, for example, if you want to see moments, directly you can link to moment by clicking the timestamp given in the description of this video. So, it's easy to access the whole video in terms of the subtopics I am going to discuss. Okay, so first you should know what is force. IGCSE, you would have learned that force is a physical quantity that can change the shape of an object, or that change the acceleration, or that change the motion of an object. That is called force. And also you know force is a vector and its SI unit is Newton. Okay, so since force is a vector, all the properties belongs to vector is applicable for force also. So what are the properties of a vector? The first you should know, when you invert the direction of a vector, it will be indicated with a negative sign. So that is applicable for force also. So that means there's an object. On that object, a force of 10 Newton is acting towards right or towards east. So the same force, or I can name this F equal 10 Newton. So the same force could be shown on the same object, this direction, F equal minus 10 Newton. That means when the direction of a force is inverted, it will be written with a negative sign. That is the first property of a vector. Since force is a vector, force also has that property. When you invert the direction, it will be written with a negative sign. That's the first property. Then the second property, a vector can be written or can be shown by a straight line with an arrow according to a scale. So that means force also can be shown by a straight line with an arrow. For example, there is an object. On that there is a force of 20 Newton acting towards east. So this force could be shown by a straight line with an arrow based on a scale. So I can define a scale, say 4 Newton is equal to 1 centimeter. That means 20 Newton equal to 5 centimeter. Then I can represent this 20 Newton force which is acting towards right by a straight line. I should measure and draw by a straight line which has a length of 5 centimeter with an arrow towards east. Okay, so the force could be shown by a straight line with an arrow which has a length of 5 centimeter. That is the second property of a force, because that is the property of a vector. A vector could be shown by a straight line with an arrow. Okay, so the third property, all the vectors obey a rule called vector addition rule. So the vector addition rule is used to find the resultant vector of system of vectors. So here, what do you mean by resultant vector? So here we consider the resultant force. When an object is under action of system of forces, we can find the resultant force by using vector addition rule. So when we draw the vector addition rule says, we can show the same thing what I told. A force could be shown by a straight line with an arrow. We can draw a vector diagram or vector polygon such that a second vector should be drawn from the end of the first vector. Third vector should be drawn from the end of the second vector. Fourth vector should be drawn from the end of the third vector, such that we can complete a vector diagram. Then we should connect the most initial point and the last point. That line indicates the or gives the resultant vector in force. That will give the resultant force. And rather than telling too much of sentences, I'll show an example. Okay, so this could be the question, the first question. Two forces 12 Newton and 8 Newton are acting at an angle 30 degree among them. 12 Newton is a horizontal force, 8 Newton is making an angle of 30 degree with the 12 Newton. We need to find the resultant force of these two forces by drawing a vector diagram. Okay, so how to find the resultant force by drawing a vector diagram? First, we should define a scale. I already told that you can show or represent a vector, that is a force, by a straight line with an arrow. So we should define a suitable scale here, so such that that could be drawn on your notebook. So the answer I write that. So the scale, I can define the scale like 2 Newton equal 1 centimeter. So 12 Newton will be equal to 6 centimeter and 8 Newton will be equal to 4 centimeter. Okay, so after that, if there is a horizontal force, better draw that first because easy to draw horizontal line. If there is a vertical force without horizontal force, better draw vertical line because that also easier to draw, right? So here 12 Newton is the horizontal force. We will draw 12 Newton to represent. We draw a 6 centimeter length in horizontal direction. You should measure 6 centimeter by using a rule and draw a length of 6 centimeter. So that represents 12 Newton force. Okay, so vector addition rule says the second line, the second vector should be started from the end of the first line. So the end of the first line is this one. So I can name, if you want, I can name this A, B. So AB, the line AB represents the force 12 Newton. A is the starting point, B is the end point. So I should draw the next force, which is 8 Newton from B, not from A, it should be started from B. Okay, so when I draw that line 8 Newton, it should be parallel to this force. So how to identify its parallel? You can see that the line, this one, the force 8 Newton is in anti-clockwise direction 30 degree from 12 Newton, is it? It's at 30 degree from 12 Newton in anti-clockwise direction. So from B, I should draw the same line here that has a length of 4 centimeter. So from B, I should draw, so extrapolate this line AB, and from this line, I should measure 30 degree in anti-clockwise direction to represent 8 Newton and draw a line of length 4 centimeter. So measure this 30 degree and draw a line of length 4 centimeter. So that represents the force 8 Newton. Okay, so that will be the second force. Now connect the most initial point and the last point. So connect A and C. You connect A and C, that will be the resultant force FR. So measure the length of AC. So when you measure the length of AC, you will get, after drawing properly, use a sharp pencil, right? So if you measure, you will get 9.7 centimeter. That means 1 centimeter and 2 Newton means the resultant force, you have to multiply this by 2 according to scale. So it will be 19.4 Newton. That's the resultant force. So when you say the resultant force, we should tell its direction also. So measure this angle. Measure this angle. I can name it theta. So theta will be, when you measure, you will get that theta will be equal to almost 12 degrees. So that means the resultant of these two forces is 19.4 Newton that acts at an angle 12 degree with horizontal line. That is the resultant force. So I drew this vector diagram based on vector addition rule. So the vector addition rule says the second vector should be started from the end of first vector, third should be started from the end of second vector, and so on. Connect the most initial point and the final point. The line, the direction of the resultant should be from the most initial point to the final point. From the most initial point to the final point. That's the direction of the resultant force. We'll do more questions now. Okay, so this is the second question. Three forces are acting on an object. 15 Newton is a horizontal force, 12 Newton is a vertically downward force, and the 24 Newton that makes an angle 60 degree with the horizontal force. So there are three forces acting on it. Okay, so when you are drawing, I told you it's better to start with horizontal force. Then the second force, which one should I take? You might think. So should I draw 15 Newton first? Then which one should I draw second? You can draw either 24 Newton or 12 Newton second. Then third, you can draw the other one. Okay. Whatever the order you draw, it won't go wrong. The final answer and the final alignment of the resultant force will be the same. So I'll go in this order. So here I'm going to draw this order. 15 Newton I'll draw first. Then I'll draw 24 Newton secondly, and third, finally, I'll draw 12 Newton. But if I draw other way, the shape will be different, but the direction and the magnitude of the final resultant force will be the same. I'll do both methods, you'll get the same answer. Okay, so here we should define a scale, suitable scale. So 24 Newton is a if I take 1 Newton equal 1 centimeter, 24 centimeter length, you can't draw. So we'll take a scale something like this, 3 Newton. So scale we will take 3 Newton is equal to 1 centimeter. So 24 Newton will be equal to 8 centimeter. And 15 Newton equal to 5 centimeter. 12 Newton equal to 4 centimeter. So these are suitable scale. I feel this is better length, so you can easily draw. So first I will draw 15 Newton, so that must be drawn with a length of 5 centimeter. So draw 5 centimeter length first. You can name A, B. So this is the first force, 15 Newton, I draw it. Okay, so second I am going to draw 24 Newton. So it must be at an anti-clockwise direction 60 degree. It's at 60 degree anti-clockwise direction from 15 Newton. The rule says I should draw the second line or second vector from the end of the first vector. So B is the end of the first vector, that is 15 Newton. So from B I should extrapolate and I should draw the 24 Newton at anti-clockwise direction to an angle of 60 degrees. So measure, keep the protractor here. So keep your protractor like this here. Measure 60 degree and draw a length of 8 centimeter. So 8 centimeter draw from here. This is 60 degree. This should be 8 centimeter length of line. Okay. So then I should draw the 12 Newton force, which is vertically down. But vertically down, how can I confirm it? From this point, look at here, from this point, this 24 Newton, 12 Newton is, see, look at here, from 24 Newton, 12 Newton is in the clockwise direction 150 degree, because this is 60 degree. This is 90 degree, 60 plus 90, 150 degree. So from the 24 Newton force, 12 Newton is in the clockwise direction, 150 degree. So there you should extrapolate it. So extend this line. Then from that line, measure little long, it should be 8 centimeter, no? Little longer. Right. So from this extrapolate it, okay. Then measure 150 degrees. So keep your protractor here and measure 150 degree in this direction, clockwise direction. Measure 150 degree, and if you draw, you will get exactly a vertical line. So measure 150 degree from there and draw a line that will become vertically downwards. Draw a line of length that is 12 Newton means 4 centimeter. Draw a line of length 4 centimeter. So that will be AB, this is C, this is ending at D. Okay. Then connect the most initial point and the final point. That will be the resultant force. So connect those two lines. So connect the most initial and the final point. that will be AD. A to D is the resultant force. So this will be almost, we should show the resultant with double arrow. So double arrow, that will be the resultant force. The length of line BD gives the resultant force. So this must be, this will be 150 degree in clockwise direction. Extrapolate at point C and measure 150 degree clockwise direction, because from this force, this is 150 degree. So from here to here, 150 degree. Okay, so measure the length of AD. So the resultant force FR is the line AD, A to D. If you measure the length, you will get that length will be equal to 9.5 centimeter. That is 1 centimeter represents 3 Newton. Multiplied by 3, you will get 28.5 Newton. So that's the resultant force. And the resultant force, normally we should give the direction. So you can measure this angle, measure it theta. So measure this angle theta, you will get 18 degree. So that's the resultant force. Okay, so method 2, so I'll keep this on board, and same scale, method 2, here I drew first this one, then I drew this as the second, this is the third. Now I'm going to draw the other order. So this is first, I'm going to draw 15 Newton first, this one I'm going to draw secondly, then this will be, finally I'll draw the third force will be the 24 Newton. See, we'll see what's the shape. It will be a different shape, but final answer will be the same. There's no change in final answer. Okay, I'll raise the question. Okay, so same way I'm going to draw. First, I'm going to draw 15 Newton. So draw the 15 Newton first. That is to represent, it should be represented by a line of length 5 centimeter. 5 centimeter. Right. Then from end of this, I can name it AB. So at B, I should draw the second force, 12 Newton, that is vertically downwards, means 90 degree. The angle between 15 Newton and 12 Newton, 90 degree. So measure 90 degree, keep your protractor here, and measure 90 degree and draw the line vertically downwards, a length of 4 centimeter. Line of length 4 centimeter, draw it vertically down, 4 centimeter. I'll put it on the left side. Yeah. Right. Then I should draw finally this force from this point C. Okay, what should be the angle? From this force, this is at an angle. You can see this angle how much? 150 degree. So that means from here in anti-clockwise direction, from 12 Newton to 24 Newton in anti-clockwise direction, 150 degree, 150 degree. So extrapolate it, extend this line, keep your protractor here and measure 150 degree in this direction, in anti-clockwise direction, this way, measure 150 degree and draw a line of length 8 centimeter. So measure this way, from here measure 150 degree, right, and draw a line of length 8 centimeter. That will represent the force 24 Newton. So this way, draw it. This angle 150 degree. Draw a line of length 8 centimeter. So connect the most initial, so I can call this D. Connect the most initial and the final points. So that will be the resultant force Fr. So you can see the shapes are different, but the length of FAD here, the length of AD is same as you will get 9.5 centimeter. There's going to be any change in the final results. It will be the same, but only the shapes are different. You can see when you take the order, when you're drawing the force order, the shape becomes different. But the final answer, you draw it and see the length AD will be equal to the resultant force. FR will be, you will get same as earlier, 9.5 centimeter. That is 28.5 Newton. Measure this angle, same as here, you will get theta, this one, you will get theta equal to 18 degree here also. Okay, so this is the third question. So here also three forces acting. 24 Newton is horizontal. The 16 Newton is making an angle 40 degree with the horizontal line upwards. This is 32 Newton downwards. It makes an angle 35 degree with the horizontal line. So here also we can go in a different order. But I told if there's a horizontal force, better start with that one. So I'll draw this one first. Then secondly, I'll draw this force. This one I will draw second, then this one third. Then I can draw the other order also. Here the scale we should take 32 Newton is too large, so we can take 4 Newton. 4 Newton equal 1 centimeter. So 24 Newton, 6 centimeter. Then 32 Newton, 8 centimeter. And 16 Newton, 4 centimeter. So when you draw, your pencil should be very sharp and narrow. It should not be a blunt pencil, because even 1 millimeter can accumulate and give a big error. So better to have use a sharp, clear pencil. Okay, so first I'll draw 24 Newton. So it should be from left to right. So that's 24 Newton. AB, I can name it. So that should be length of 6 centimeter. AB. Right. So then I'm going to draw 32 Newton, that is 8 centimeter length. So it should be, you can see from this force, this is 35 degree this direction. So I can measure this. Imagine I should draw a line parallel to this one, or from here I should move in anti-clockwise direction. You know this is 180 degree, the straight line 180 degree. So this angle, you can think about this angle. How much should it be? This angle is 180 minus 35, that is 165 degree. Is it? 165 degree from 24 Newton to 32 Newton in clockwise direction. 160, sorry, I think I made a mistake. 145 degree, yeah. 145 degree. So I should measure 145 degree, because the total angle is 180. So 145 plus 35, 180. So in clockwise direction, 145 degrees. So you can extrapolate this line AB. You can extrapolate this line, extend this line. So keep the protractor here and measure 145 degree from here. Measure 145 degree from here. 145 degree from here. Measure in this direction, in clockwise direction. Then draw a line of length 8 centimeter. So that if you measure that way, 8 centimeter. So this should be, and draw 145 degree this one, and draw a line of length 8 centimeter. Okay, so it should be something like this. 8 centimeter should be longer. I can draw a straight line on the board with difficult. Right, so 145 degree, 8 centimeter length, you draw it here. So this is a 6 centimeters on the apple. Right, okay. Okay, so from C, I should draw 75 degree in, again in clockwise direction. From this end, I finish this force, 32 Newton. From that, 75 degree in clockwise direction, 75 degree. So you can extrapolate it. Keep the protractor here. measure 75 degree, measure this from this direction 75 degree. So somewhere here like this, okay, 75 degree in this direction, 75 degree, because from here to here clockwise direction 75 degree. So measure 75 degree and draw a line of length. This is 75 degree. Draw a line of length that represents 16 Newton, 4 centimeter. That is D. So this is the most initial point. This is the final point. Connect from A to D, from initial to final. So connect these 2 points. So this will be the resultant force. The length of line AD is the resultant force. You can measure it. You will get resultant force will be equal to 4.2 centimeter. That will be equal to 16.8 Newton. And the direction, you can give the angle with this one, or you can measure this angle, one of it you can measure. So if I measure this angle with horizontal line, that angle theta will be equal to 151 degree. Okay, so you can draw in other order, the next way, the first, second, third. The shape will be different, but the final answer will be the same. So first, this as the second vector, and this as the third vector you draw. The shape will be different, but the final answer, the orientation and the magnitude of the resultant force will be exactly the same as this one if you draw this order, first, second and third. So if I draw it, I'll draw that method here. So 24 Newton should be drawn with 6 centimeter length. Board space enough, I think, 6 centimeter. This is AB. Then second, I should draw this one 4 centimeter. So you can measure this angle, or even if you can measure inside it, it's geometry, O-level geometry, simple thing. If you think about this angle, so from this line you can extrapolate it and measure this angle, that is 140. This is 140. Right? So 140, keep your protractor here, measure 140 in anti-clockwise direction, 140, measure it and draw a line of length. This is 140, or you can measure this as a 40 degree. Either way, it's not a big issue. You can draw this line, a length 4 centimeter. This is 140. You can mark in anti-clockwise or in this direction inside. You can measure 40 degree. Either one you can draw. You can measure. Then what we draw? Then draw a line of length 8 centimeter. From here we should draw. This is C. So extrapolate it. Now what's the angle from here to here? From this one in anti-clockwise direction. 75 degree. So anti-clockwise direction, measure 75 degree and draw a line of length 8 centimeter. So measure, keep your protractor here. Measure 75 degree in this direction, measure 75 degree and draw a line of length 8 centimeter. So something like this you will get 8 centimeter. I think it's a little inside. Drawing, you try it. I am drawing without any measurements. 75 degree, measure it. Something like this. Okay. Something like that. 75 degree. And draw a line of length 8 centimeter. That will be the D. Now connect A and D, these two. That will be the resultant force. So you can see the orientation, you will get exactly the same. If you measure and draw, you will get exactly the same orientation. Here also you can measure this angle. You can measure this angle. You will get 151 degree here. The shape will be different, but the final answer and the orientation of the or the alignment of the resultant force will be the same. Okay, so this is the way we can find the resultant force by drawing vector diagrams based on vector addition rule. This is one of the methods to find the resultant force. The second method, the next method, we can find the resultant force by resolving the vector. So that's the next topic we are going to do, how to resolve a vector. That is the property of a vector. Resolving a vector is also the property of the vector, so it's a property of a force. We can resolve a vector in two right angle direction, or generally horizontal direction and vertical direction. So force also could be resolved into two right angle direction, generally horizontal direction and vertical direction. We resolve a force because force is a vector. That is the next property of the vector. Okay, so the next topic is about resolving a vector into two components, means two perpendicular components. I didn't write perpendicular, whatever it is. So two perpendicular components or two right-angled components. Okay, say for example, what do you mean by resolving a vector? Say for example, if there's a force is a vector, so I'll take F is a vector that makes an angle theta with horizontal. So you know that the force F could be shown by a straight line with an arrow according to a scale. So the force F is shown by a straight line with an arrow, right? I can draw a right angle triangle by using this given force. I can complete a right angle triangle like this. So F is the given force that makes a given vector, or I'll talk about force because our aim in this topic, in this video, is about forces. So force is a vector. This is general for any vectors, what I am telling. So F is a vector which is force, and that makes an angle theta with horizontal line. So I can show it by a straight line with an arrow. So I drew it by a straight line with an arrow. So now I can complete a right angle triangle by using this line F. So if I complete a right angle triangle like this, and I'll name it A, B, C. Okay, so in this right angle triangle, sine theta is equal to opposite BC over this line AB. AB is F. So BC is equal to F sine theta. Same way, cos theta is equal to AC over AB. AB represents the vector, that is force F. So AC equal F cos theta. So now I can think about drawing two perpendicular lines. What are they? BC and AC. So if I draw BC this way, BC, that is F sine BC. Okay, I'll name it as BC. Sorry, AC. I'll draw the AC first. AC. Then BC from here, BC. So that is CB, no? Actually, I think it should be CB. Sorry, I'll put it as CB. Easy to name it. CB. This represents the given force F. So if I want to get F as a resultant force, the direction of AC should be towards right, according to vector addition rule. The direction of the F cos theta should be towards right, and the direction of F sin theta should be upwards. This is F cos theta. This AC is called the horizontal component of the given force F, and F sin theta is called the vertical component of the given force F. That means it's other ways. The F is the given force that makes an angle theta. I drew and complete a right angle triangle by using the given force. So I have completed a right angle triangle. The length AC is F cos theta and the length CB is F sin theta. Now if I draw only these two lines again, CB and AC, AC and CB, so the resultant of these two lines or vectors should represent the force F. So these two lines are called These two lines are called horizontal component and vertical component. All these two lines are called generally two perpendicular components of the given force F. Okay, so actually it's based on geometry. Actually, it's a geometry shows that F is the given vector, means its horizontal component here is F cos theta, the vertical component is F sin theta. Similarly, the same force I can consider with an angle alpha with vertical line, something like this way. If the given force is F, that makes an angle alpha with vertical line. So here also I can complete a right angle triangle like this. A, B, C. The line in this one's sine alpha, in this right angle triangle, sine alpha equal AB over F. So AB equal F sine alpha. Same way, BC equal, or I can say cos alpha in this right angle triangle, cos alpha equal BC over AB, that is F. So BC equal F cos alpha. So if I draw again the line AB and line BC, AB and BC, to get the F as a resultant force, this should be this way, this should be this way. These two, AB, that is F sin alpha is the horizontal component of the given force. F cos alpha is the vertical component. This F cos alpha is the vertical component. This F sin alpha is the horizontal component of the given force F. So angle alpha is this one. Okay, so components mean we resolve or split the given force into two right angle directions. Generally, we take them into horizontal and vertical directions. So we normally resolve a given vector into two perpendicular directions, generally horizontal and vertical directions. So easy to remember. The component that is with the angle measured will be given with cos. The component which is opposite to the angle will be given with sine. So generally you can remember that like this. Generally you can remember like this way. If the given force is F this way, at an angle alpha, the horizontal component, that means the horizontal component, how to get the horizontal component here? You can simply keep the pen with the given force. To get the horizontal component, you know horizontal is this line. To get the horizontal component, I should close this one to the horizontal line. When I close it, it gives the horizontal component. And if you keep the pen along the arrow, and when you close it, the nib is pointing to the right. Keep the nib along the direction of arrow, and if you close it, it points to the right. So the horizontal component will be F cos alpha, this direction. Same way, keep the pen. To get the vertical component, here I should move it away from the angle alpha. When I move it away, it's pointing upward direction. So F sine alpha is the vertical component. If I have two vectors towards right and up, I know the resultant vector is F. So this is the resultant vector of these two. Its components are these two. Both are true. Resultant vector of F cos alpha and F sin alpha is F. Same way, the components, horizontal component of F is F cos alpha, vertical component F is F sin alpha. Now if I consider the second example, this way, there is a force or vector this direction F that makes an angle with vertical line theta. How to find its horizontal and vertical component? So to get the horizontal component, you can keep your pen like this. You can keep your pen along the arrow, keep the nib. To get the horizontal component, I should move it away from the given angle. It's point to the left. So the horizontal component will be this direction. F, away means side. To get the vertical vertical component, what should I do? Keep the pen along the arrow. I should close it through the angle. Close it through the angle. Close it through the angle. Close means cos f cos theta. So simple, I already explained that. Simply the geometry. Again, I'll explain in terms of geometry. This is the f. This is the angle theta. Complete a right angle triangle about it. So name it A, B, C. Here the horizontal component is the line CB. If the arrow is this way, the horizontal component should be this way, CB. CB, that means if I say sine theta is equal to CB over F. So CB is equal to F sine theta. That is the horizontal component. The vertical component, the length AC. So length AC means cos theta equal AC over F. So AC equal F cos theta. That's actual theory. That's actual theory, the geometry. But for simplicity, too easy to do quickly, we tell the students to keep the pen along the arrow. To get the vertical component here, I should close it. To get the vertical component, I should close it through angle theta that points downwards. Close it means cos. Away means to get the horizontal component, I should move it away. Away means sine. That's the way we normally tell to keep it in mind and to write it quickly. But actual theory is this one. Complete a right angle triangle around it. To get the resultant this way, this should be this way and this should be this way. This plus this gives this one. Simply, that's a geometry actually. But we normally tell the shortcut to remember and do faster. So this is the AC, is the vertical component, F cos theta, which is downwards. CB is the horizontal component towards left. Better to know the actual reason, what do you mean by horizontal and vertical components. So better to know that also, but we normally teach in a shortcut method. Okay, so we'll do questions related to resolving a vector into horizontal and vertical components. So I drew the diagram for the questions. Okay, first question. There's a force F1 that makes an angle theta with horizontal. So keep your pen along the direction of arrow. To get the horizontal component, you should close it through angle theta. Close it. See, symbol like that. Close it will be cos, it's pointing to the left. So its horizontal component will be towards left. So its horizontal component will be towards left. F cos theta. F1 cos theta. To get the vertical component, what should I do? I should move it, keep the pen along the arrow. The nib should point the direction of the force. Move it away from the acute angle. Always consider the acute angle. Move it away from the acute angle. It points downwards. Move it away means, remember, sine. So the vertical component downwards, F1 sine theta. Okay, in the second example, keep the pen along the arrow. The nib points in the direction of arrow. To get the vertical component, move it through or move it, close it through angle alpha. Close it through angle alpha, pointing upwards to get the vertical component. So keep the nib along the arrow, close it through the acute angle alpha. It's pointing upward. Close it means cos. So this direction, F2 cos alpha. Same way, to get the horizontal component, move it away from the, or open away from the given angle. It point to the right. Keep the pen along the arrow. Open it away from the angle. It point to the right. Away means sine. So the horizontal component F2 sine alpha. Same way here. Keep the pen along the arrow. To get the horizontal component, close it through the angle theta pointing to the left. So horizontal component will be towards left, F3 cos theta. To get the vertical component, keep the pen along the arrow, move it away or open away from the angle theta, it's pointing upwards. So the vertical components, sine, vertical component, F3 sine theta. This one is already a horizontal vector. Remember that horizontal vector has no vertical component. So it has only horizontal component, which is F4. So that means we can say like this: a horizontal vector has no vertical component. Same way, a vertical vector has no horizontal component. So that means it has only the vertical component. What vertical vector means? That's the vector. It has no horizontal component. Same way, horizontal vector has no vertical component. So simply we can say a vector cannot be resolved through 90 degree. A vector which is horizontal cannot be resolved through 90 degree to get a vertical component. So here I resolve it. So I resolve here. This one I can say I am resolving it in vertical direction to get the vertical component. I am resolving it to horizontal direction to get the horizontal component. Here I am keeping the pen like this. I am resolving in horizontal direction to get the horizontal component and resolving it to vertical direction to get the vertical component. But here I can say the horizontal vector cannot be resolved into vertical direction. Vertical vector cannot be resolved into horizontal direction. So simply I can say a vector, that means a force, cannot be resolved through 90 degree. Important conclusion. Later we can use this idea for questions depending on the question. So remember that a vector cannot be resolved through 90 degree. Keep it in mind. Okay, so we are going to learn the application of resolving a vector when we calculate the resultant force. So an example, the same as the first question, I am repeating it as the fourth question. Here I am going to find the resultant force by resolving the vector or given forces into horizontal and vertical direction. Okay, so to do that, first I should resolve all the given forces into horizontal direction and find the total horizontal component. Then resolve all the given forces on the diagram into vertical direction and find the total vertical force. When you know the total horizontal force and total vertical force, imagine that you are sketching a vector diagram. Then we can use the Pythagoras theorem. Okay, we'll come to that point. But first we'll resolve all the given forces into horizontal direction. So when you are resolving all the given forces into horizontal direction to find the total horizontal component, define one of the direction, either left or right, as a positive. So when you resolve a vector or resolve a force into horizontal direction, say for example you are taking towards right positive. So I will take towards right positive. I will take x means the total horizontal direction, total horizontal component x. And if anything towards right, I am going to take it positive. So if I want, I can take it towards left also positive. That is nothing wrong. But I am just taking towards right positive. For when I resolve any of these things, if I get towards right, I'll write it with positive. If I get towards left, I'll write it with negative sign. Okay, so I'm going to resolve everything in horizontal direction. If it is towards right, I'll take it positive. Towards left, I'll take it negative. Okay, so one by one, 12 Newton is already in horizontal direction, so I should write 12. Then 8, I should resolve it. To get the resolved horizontal component, move it, close it through the angle 30, pointing to the right. So plus, it's pointing to the right, I'm taking towards right, positive. So it will be 8 cos 30. Find the total horizontal component, you will get 18.93. Then find the total vertical component. I am taking upward direction positive. No reason. I can take downward direction positive means then upward direction will be negative. No reason. I am just taking upward direction positive. So anything towards down will be negative. Okay, so I am taking upward direction positive. I'll denote by y. Okay, one by one we'll take it. This is a horizontal vector. Just now only I told horizontal force has no vertical component. You can't resolve a force through a horizontal. That means you can't resolve a force through 90 degree. Horizontal force has no vertical component. So this has no vertical component. I should put 0, but not necessary to put 0. I'll just leave this. So this has no vertical component. Then this one, what should be its vertical component? keep the pen along the arrow. To get the vertical component, open it or move it away from the angle pointing up. Away means sine 8 sine 30. That will be 4 Newton. Okay, so now I have two perpendicular right angle vectors or right angle forces. What are they? Horizontal force towards right 18.93, vertical force which is upwards 4 Newton. So if I imagine I am sketching a vector diagram, the horizontal should be towards right, that is 18.93, and this is vertical upwards 4 Newton. So if I draw a vector diagram, I should draw that represents the 18.93 horizontally and 4 vertically, means I will get a right angle triangle. So the resultant force will be from the starting to finishing. I am not drawing, I am sketching. I am not using a scale diagram. I am just imagining, I am drawing. I imagine I am drawing 1 Newton equal 1 centimeter. Like that I imagine, I am not drawing it. So if I imagine like that, I would have drawn 18.93 centimeter length and 4 centimeter length. It will be a right angle triangle. If I connect starting and the final line, that will be the resultant force. So what will be this length? I don't need to draw actually. I don't need to draw according to scale because I can simply use Pythagoras theorem. Imagine again, I am saying I am not drawing but I am sketching. I imagine I am taking 1 Newton 1 centimeter. So when I imagine 1 Newton equal 1 centimeter, I would have drawn 18.93 centimeter length to represent 18.93 force. Then I would have drawn 4 centimeter length to represent 4 Newton. This is 90 degree. Then I should measure this length, but I know that it's a Pythagoras theorem I can use because these two forces are perpendicular among them. So I don't need to draw. I can directly use Pythagoras theorem. So if I use the Pythagoras theorem, that is Fr, the resultant force will be equal to square root of 18.93 square plus 4 square. So that means, imagine again, I am using 18.93 centimeter, 4 centimeter to get this length when I use 1 Newton equal 1 centimeter. I am not drawing, I am imagining like that. So Fr will be equal to how much? That will be 19.34 Newton or 19.34 centimeter. I will get it. 1 Newton equal 1 centimeter. Imagine the scale. So 19.34 Newton. Then I can use tan theta. Tan theta equal opposite 4 over 18.93. So theta equal tan inverse. You know you can use the calculator. So tan inverse 4 over 8.93. You will get around 12 degree or 11.9 degree. So that's the resultant force. Okay, so this is the second next question, that is fifth question. I am numbering from the first one. So here also find the resultant force by resolving the forces into horizontal and vertical directions. Okay, we'll resolve all the forces into horizontal direction and find the total horizontal force. So I'll take towards right positive. If you want, you can take towards left also positive. No reason. Just I am taking towards right positive. So I'm going to find the total horizontal force of this system of forces. 15 Newton is already towards right, so I'll just put 15. When I resolve this 24 Newton into horizontal direction, I should close it through 60 degree. It will point to the right. I am taking towards right positive, so it should be plus 24 cos 60. This is a vertical force. I told if you have a vertical force that won't have any horizontal component, or a vector cannot be resolved or force cannot be resolved through 90 degree. Vertical vector has no horizontal component. So that's all the total horizontal force. So 15 plus 24 cos 60, that will be 27 Newton. Total vertical force, I will take it upward direction positive. One by one we will take it. This is already a horizontal force that has no vertical component. So it should be 0, but I don't need to show 0. I will just leave it. This one, if I resolve it in vertical direction, it will point upward direction. Move it away or open away from 60. Sine. Away means sine. So that will be 24 sine 60. This is already a horizontal, a vertical downward force. I am taking upward positive, so minus 12. So when you solve, you will get the vertical force 8.78 Newton. Okay, so the total horizontal force, if I sketch a vector diagram for these two right angle forces x and y, x is towards right 27 Newton, y is upwards 8.78 Newton, which is 90 degree. So I imagine I draw a vector diagram taking a scale 1 Newton equal 1 centimeter. So I would have drawn 27 centimeter. I would have drawn 8.78 centimeter in vertical direction. So the resultant should be along this line. That's the resultant force Fr. So everything 1 Newton, 1 centimeter, 27 Newton, 27 centimeter, 8.78 Newton, 8.78 centimeter. So it is a right angle triangle. So actually I don't need to draw, because right angle triangle means I can use Pythagoras theorem. So the resultant force Fr, I use Pythagoras theorem, square root of 27 squared plus 8.78 squared. So the resultant force will be equal to 28.4 Newton. In this right angle triangle, the direction of the resultant force theta, so tan theta equal opposite 8.78 over 27. So find the theta, that will be equal to 18 degree. Okay, so this is the sixth question, same as earlier. We need to find the total horizontal force and the total vertical force. So we'll resolve it horizontally. I'll take towards right positive. I'll find the total horizontal component x equal. This is already horizontal, so 24. When I resolve this horizontal, it's going to point towards left. So close it through 40. It's pointing to the left. So I'm taking towards right positive. So minus 16 cos 40. Same way, if I resolve it horizontally, I should close it through 35 degree. It will point to the left. So minus 32 cos 35. So when I resolve it, it will be total horizontal force will be minus 14.5. Towards right, I took it positive, but I am getting minus. So I told one of the properties of vector, if it is minus, I should invert it. If I invert to the left, it will be positive. X will be 14.5 Newton. If I invert it, it will be minus 14.5. Minus into minus 14.5. So plus 14.5 towards left. When I resolve vertically, I'll take upward direction positive. Y is equal to, so the vertical component, this is already horizontal vector. Horizontal force has no vertical component, so I don't need to put 0, not necessary. This one, if I move it, open it or move it away from the angle, it will point upwards. So that means 16 sine 40. When I resolve it, it will point downwards. I am taking upward positive downwards. So minus 32 sine 35. So when I solve it, you will get minus 8.07 Newton. Upwards minus means downwards. I had to invert the direction. So downward direction, y equal 8.07 Newton. Okay, so I'll sketch a vector diagram by assuming 1 Newton equal 1 centimeter. So towards left, 14.5 Newton means 14.5 centimeter. Vertically downwards, 8.07 means 8.07 Newton means 8.07 centimeter. Imagine like that, 8.07 centimeter or Newton, whatever it is. So the resultant will be along this direction. That's the resultant force. So 14.5, 8.07 Newton or centimeter, because I assume 1 Newton equal 1 centimeter. I am not drawing, I am sketching. So I can draw, I can find the resultant by using Pythagoras theorem. So FR, the resultant force, is equal to square root of 14.5 squared plus 8.07 squared. That will be equal to 16.8 Newton. This angle you can find it theta. So tan theta equal opposite 8.07 over 14.5. From this theta equal tan inverse, take it. You'll get 29 degree. Okay, so next is Newton's laws of motion that you are learning from IGCSE. You know there are three laws. Newton's first law, what is it? You know that Newton's first law, it says that object which is at rest will remain at rest, and the object which is moving at a constant velocity will continue to move at the same velocity unless it experiences an unbalanced force. That is the Newton's first law. Again I am saying Newton's first law says object which is at rest will remain at rest, and the object which is moving at a constant velocity, not speed, constant velocity, will continue at the same velocity unless it experiences an unbalanced force or resultant force. That is the Newton's first law. Newton's second law, it relates, it's a mathematical format. Resultant force equal mass times acceleration, or F equal ma, where F is the Newton, mass should be in kilogram, A is the meter per second squared. That is the Newton's second law. Third law, what it says, when object A exerts force on object B, the object B also will exert the same magnitude of force on A in opposite direction. Again, when object A exerts force on B, they might have different mass, whatever it is. When A exerts force on B, B will exert same magnitude force on A in opposite direction. So these two forces are called Newton's third law pair of forces. These Newton's third law pair of forces have some properties. You must remember them. What are the properties? First one, they have the same magnitude. So the properties of Newton's third law pair of forces, you must know. What are they? First, you should know those two forces have the same magnitude. Same magnitude. First one. Second one, they act for the same time. They act for the same time. Third one, act on two different objects. Fourth one, they act in opposite direction. Fifth one, they act on the same line or along the same line. Sixth one, they will be the same type of force. They will be the same type of force. So these are the properties of the Newton's third law pair of forces. So they act for this, they will have the same magnitude, the pair of forces. Object A exerts force on B and object B exerts force on A. So these two forces are called Newton's third law pair of forces. So they have these properties, same magnitude, they'll act for the same time period. Two different objects, they won't act on the same object, they will be exerted on two different objects. Then they always act in opposite direction to each other. Along the same line they will act, and they will be the same type of forces. If A exerts gravitational force on B, B will exert gravitational force on A. If A exerts electromagnetic force on B, B exerts electromagnetic force on A. So like that, they will be the same type of forces. The type of forces you already learned in IGCSE, so I am not going to deal about that, the type of forces. So they will have the same type of force. Okay, now when we consider Newton's first law and second law again, actually you know Newton's first law is included in the Newton's second law. So again, if you carefully note that the Newton's first law and second law, you can see that Newton's first law says that object which is at rest will remain at rest, and the object which is moving at a constant velocity will continue to move at the same velocity unless it experiences an unbalanced force. That's the Newton's first law. Second law says F equal ma, where F is the resultant force and A is the acceleration. So actually, we can show that even in the Edexcel past paper they asked it twice, I think. A student says that the question was like this. A student says that the Newton's second law includes the Newton's first law. Justify the statement. Yes, how can we show that statement is correct? That is, Newton's second law includes the Newton's first law. That means from the second law we should be able to get the first law. If we can get it, they are both actually almost same, I can't say, but the second law includes the first law. Say for example, according to Newton's second law, we know that F equal ma. Sorry, F equal ma. A is the small. So if A equals 0, that means if the acceleration equals 0, then I can say like if A equals 0, if the object has no resultant force, if F equals 0, then A equals 0. If equals 0, then A equals 0. Right. We'll take that condition. So if the object is already at rest, so if U is 0, if the object is already at rest, then according to V equal U plus AT, you know that equations of motion. So when the resultant force is 0, according to Newton's second law, if the resultant force is 0, then acceleration will be 0. If the object is at rest, U is 0. Initially, if the object is at rest, then according to V equal U plus AT, later at any time t, then V equal 0 at any time t. So that means when the resultant force is E0 and if the object is at rest, it will remain at rest forever. At any time t, V equals 0. That means later at any time t, V equals 0 means later it will be always at rest. Then if U is not equal to 0, then according to V equal U plus AT, when you consider, what will happen? V equal U plus, it's a non-zero value, it has a value, but no acceleration. When the resultant force equals 0, no acceleration into t. So that means at any time t, the velocity will be equal to U. That means if the resultant force equals 0, acceleration is 0, and if the object is already in motion, so U is non-zero value, then at any time t, the velocity will remain same as, we substitute here A0, V equal U, at any time t, the velocity will be equal to U. So object which is at rest will remain at rest. You can see when the object is at rest, will remain at rest at any time. The object which is in motion, which has non-zero value, motion, will continue to move at the same velocity u at any time t. So we can show this way that Newton's second law includes the first law. Okay, so next thing, free body force diagram. Free body force diagram shows all the forces acting on an object. So maybe this we call situation diagram. So there are two objects involved. One is a weighing scale and an object. An object is kept on the weighing scale. Okay, I can ask you to draw the free body force diagram for the object. Then I can ask you to draw the relevant third law pair of forces. So okay, we'll think like that. So free body force diagram, if I draw for the object, all the forces acting on the object, I should show that. So this is the object. So what are the forces acting on it? First, the weight. What is weight? The earth pulls the object down, so the weight of the object will act on the object. Careful. If you ask IGCSE student, when an object is kept on the weighing scale, what the force acting on the weighing scale, they say weight of the object. That is wrong. Weight of an object will act on that object, because weight is pulled by a planet. Say we talk about Earth, so Earth is pulling the object down. So the force exerted by the Earth, the gravitational force exerted by the Earth on the object will act on the object. So the weight of the object will act downwards due to pull by Earth. So this is the weight of the object. So that won't act on anything else. It will act on the object. Weight of an object will act on that object. So if I think about the third law pair. So or I call Newton's third law. When object A exerts force on object B, the object B will exert same magnitude of force on A. That shows all the forces are paired. You can't find a single force. So when Earth pulls the object down, if I think about the Earth, so this is the Earth. So object will pull the Earth upward direction with the same magnitude. So the object will pull the Earth upward. I can call pull by object. That also will be the gravitational force. What will be the numerical value? If this is mg, that also mg. If this is 10 Newton, that also 10 Newton. Okay, so these two are Newton's third law pair of forces. So if this is the only force acting on the object would have fallen down. So what will happen? Object is kept on the weighing scale, the balance. So if I think about the balance, the weighing scale, so the object will try to fall down, because if this is the only force acting on it, but object is not falling down. So what will happen? The object will push the weighing scale downwards. So the object will push the weighing scale downwards. I can call that push by object. So when the object pushes the weighing scale downward, it's a contact force. According to Newton's third law, the weighing scale will push the object upward direction. The weighing scale will push the object upward direction. That is called normal reaction, or even I can call it as push by weighing scale. Normally we call the force acting on the object in upward direction normal reaction. Normal reaction. So if it is R, the numerical value R, this also will have the value R. That also will have the value R. Okay, so now remember, keep it in mind, which force does it read? The weighing scale never reads the weight. Weighing scale reads always pushed by the object. Okay, always the weighing scale reads the push by the object, not the weight. It could be equal to weight. We'll come to that point later when I think about Newton's second law, but I'll do a few questions later to that. But here I can say the weighing scale reads the push by the object. The weight of the object will act on the object. Weighing scale reads the push by the object. So the force acting on the weighing scale downwards is pushed by the object. That will be read by the weighing scale. Okay, so here from roof on a light string, an object is hanging. So we can ask you to draw the free body force diagram for the small sphere. I can ask you to draw the free body force diagram for the sphere, free body force diagram for the light string. Okay, roof I am not interested, because free body force diagram, roof is attached to some other building, so we don't need to consider, but I can show the third law pairs. Okay, one by one we'll draw the object, string, and any required or relevant forces acting on the roof also we can show based on Newton's third law. So first I'll think about the object. So this is the object, the string, and the roof. I need to consider earth also if I think about the third law pair of forces. Anyway, one by one we will start. Okay, the object has its weight. So the weight of the object means earth is pulling the object down. So that will act on the object, that is mg. So I told that already. Weight of an object will act on that object. It won't act on something else. Say for example, when you are sitting on a chair, your weight won't act on the chair. Your weight will act on your body, because weight means earth is pulling your body down. So what force will act on the chair when you sit on a chair? You are pushing the chair down. The force exerted by you, contact force, right? Push by you is the force acting on the chair. Careful. O-level students, they tells normally force, our weight will act on the chair. It's a wrong statement, right? Okay, so the object is pulled by earth downwards. That is called weight of the object. If I want to draw the third law pair of this force, then I should draw earth. So that's earth. So earth pulls the object down. So object will pull the earth upwards. So I can say pull by object. What will be the magnitude? That also mg, because according to Newton's third law. Okay, I'm using the same color for third law pair of forces. Right, I'll try to use the same color. Okay, so next what happens? Object, if this is the only force acting on the object would have fallen, but it's not falling. It's at rest, hanging from a string. So what will happen? The object will try to fall down. So it will pull the string downward, a stretching force, a contact force. It will pull the string down. So this could be called as pull by object, but normally stretching force on a string is called tension, or I can say pull by object, or we can call tension, normally denoted by T. Okay, so when the object pulls the string down, the string will pull the object up due to Newton's third law. When the object pulls the string down, string will pull the object up. So this I can call as pull by string, or I can call tension, that is T. Both will have the same magnitude. I drew with the same color, red color. Okay, so object will pull the string down. That is the pull by object on the string. So string will pull the object, pull by string on the object, or generally we call tension. Right, okay. Now the object has only these two forces. If the object is at rest, they should balance each other. That will come to that point later in explaining type questions. Okay, now if this is the only force acting on the string, I told a light string, so string has no weight. But if this is the only force acting on the string would have fallen down. But string is not falling down. Why? The string is attached to the roof. So string will pull the roof down. So here I can say pull by string down. Pull by string. String is going to pull the roof down. So if the string is pulling the roof down, okay, here also I can say if this is T1, this is also T1. Third law pair of force, so they should have the same magnitude, T1, T1. Okay, so if this is the only force, if the string is pulling the roof down, that force is pulled by string, I can name it T2, or I can call it as tension, but normally you put T2. Right, so when the string pulls the roof down, roof will pull the string upwards. I can call pull by roof. Pull by roof. But normally a stretching force on a string is called tension. Tension T2. Because this is T2 I marked, so this is also T2. Right. I told this string is light, no mass. Think like this. The string has no mass because light, negligible mass. There are two forces T1, T2. Okay. So string is at rest. So the string is at rest. T2 and T1 should have the same magnitude. So I can say T2 equal T1 because string is at rest. It has no resultant force. So I should say this T and T2 should have the same magnitude because it's at rest. So this is T. I can show everything T. Okay, so since the string is at rest, both will have the same magnitude. So all the forces I can show same T because all are at rest, no resultant force. Okay, so the force acting on the string is a stretching force like this. Normally, when you ask student to mark the tension on the string here, they normally mark like this. I don't know why, but they know most of the students they mark like this. These forces are actually not the forces acting on the string, but mostly when they are doing calculation and when we ask to show the force on the string or tension, they mark it like this, that direction of arrows. Imagine if these two forces are acting on the string will sag. You keep a string and if you put the force in opposite direction like this, the string would have slag. That never happens. So actually what they are marking, the force that they mark upward direction is the force acting on the object. What they mark here is the force acting on the roof, not on the string. So they are not showing the forces acting on the string when they mark like this. This is a wrong diagram. This is not the force acting on the string. They are marking partially the force acting on the object and the force acting on the roof, not the force acting on the string. Okay, because if the force acted like this on the string would slack. Okay, so this is the way the force is acting on the objects when it hangs from a roof. Okay, so the next one, on a spring balance, an object is attached and the spring balance is attached to some support, right? So the spring balance shows a reading. Which force does it show? We'll think about it. So there also we can draw the free body force diagram for the box. And we can show the relevant other forces, third law pair. So I'll think about the spring balance. And the roof. Spring balance might have its own weight due to its materials, but anyway, I'm not interested about that. Okay, so these are the three things we need to consider. If I want, I can think about the earth also when I talk about the weight of the object. Okay, so quickly I'll draw again the same thing what I drew like that. So the object has its weight. The weight of the object will act downward. So I'll call weight or mg. So that is earth is pulling the object down. So object will pull the earth up, pulled by object. That also will have the same magnitude mg because Newton's third law pair of forces. They should have the same magnitude. Okay, if this is the only force acting on the object would have fallen. It's not falling. It's attached to the spring balance. You know spring balance inside that spring. So what happens? The object will try to fall down. So it will stretch the spring inside by exerting a stretching force or tension on the spring. I can call it as tension or pull by object. Anyway, I can call, but normally we call tension, normally denoted by T. I can name it even pull by object. So when the object pulls the spring down, there will be a tension on it. So I call Newton's third law, the spring will exert the same magnitude of force on the object. I can name it pull by spring balance, but normally we put that also tension and denote by T because whatever the force here should be same Newton's third law. Okay, so if this is the only force acting on the spring balance would have fallen, but its spring balance is not falling, it's acting to the support. So there I can say pull by spring balance or pull by the whole system. The whole system is pulling it. I can say even spring balance might have its own weight due to the metal part of it. So I can say totally pulled by spring balance plus object and object. The total weight will act there. So what will happen? The object will keep the spring balance, like I can say pulled by support or roof. So this force, if I say weight of the spring balance, if I consider that weight plus weight of the attached object. So if I say the weight of the spring balance is m naught plus mg, this also m naught plus mg, where m naught is the weight of the spring balance. Okay, now look at here. The spring balance reads which force? The tension. How much of tension is exerted to its spring? That will be read by the spring balance. If the object is at rest, okay, I'll come to those type of questions separately. But if the object is at rest, Here the resultant force must be 0, T equal mg. But this T and this T are the same. Then this T should have a value or numerical value or magnitude equal to mg if the object is at rest. Otherwise, the reading will change. So remember that spring balance never reads the weight, it reads the tension on its spring. Okay. Okay, so next is about a rear wheel driven car. That means only the back wheels, the pair of wheels on the back part, the rear wheels are connected to the engine. So, or not the front wheel, not the front wheels are not connected to the engine. So, if the rear wheels are connected to the engine will rotate the rear wheels due to the rotation of the function of the engine. Okay, why the car moves? So we'll think about the wheel X, the rear wheel. So we'll draw that wheel first. Here I'm not going to consider the weight of the car downwards, normal reactions will act on each wheels, and I'm not considering that because I'm analyzing why the car moves forward, which force accelerates the car forwards when it starts from rest. Okay, that's the purpose of this diagram. So we'll think about the rear wheel, which is connected to the engine. So we'll draw the wheel first, rear wheel, and the ground. So this is the ground or road, whatever it is. That road also I will draw it. So the contact point we call X, that this is the point X. So the name of the rear wheel I'll put P, and this is Q. The rear wheel is named P. Okay, so what are the forces acting on it? There will be weight of the wheel, so I'm not considering those things, normal reactions, I don't need it. I'm analyzing why, which force moves the car from rest. Okay, so here what happens, the rear wheel is connected to the engine. So if the car wants to move this way, the wheel will rotate in clockwise direction. You know that wheel will rotate in clockwise direction. Okay, if the wheel has enough grip due to friction with the road, you can imagine the point where it's touching the ground at point X. At point X, it's touching the ground. So at point X, the wheel will try to slip to the left. Can you imagine the graph, the point at which it's touching the ground, the wheel will try to slip, but it's unable to slip because there is enough grip or friction due to the grooves on the wheel. So the wheel try to slip this direction. The wheel is rotating this way due to the engine. So at point X, it will try to slip to this direction, to the left of my hand, this side, but it's unable to slip. You know what is friction? Friction is the force that opposes the motion or opposes the intention of motion. That is called friction. That opposes the motion or it opposes the intention of motion. So the point X where I touching the ground has intention of slip to the left. So it will oppose it. So what will happen? It will oppose it means there will be a friction to the left, sorry, to the right. There will be a friction to the right because it will try to slip and move this way. The point, this one try to move this way, slip and move, but it's unable to slip because of the friction. So the friction will oppose that motion and exert the force on the wheel towards this direction. That friction is the force accelerates the car. Okay, if you think about the wheel Y, so when the force acting on the wheel to the right, that force accelerates the car. So car will move. When the car moves, the wheel Y, what will happen? The wheel Y will try to slip on it. Imagine if you keep a coin or something and try to slip it. So if you think about the wheel Y, this is wheel X. If you think about wheel Y, and imagine if you try to slip here at this point, what will happen? It will try to slip to the right. The friction will act to the left. So the friction will act towards this direction. So when the friction acts towards this direction, the wheel has connected to the axle here. So when you keep a coin somewhere, hold it at the center and give a friction this way, the wheel will rotate this direction. Understand? So actually what's happening, how the wheels are rotating the same direction. What's the reason? The wheel X, which is connected to the engine, is rotated by the engine. So when it is rotated by the engine, it will try to slip at that point this way. Friction exerts a force opposite to the possibility of friction, possibility of slipping to the right. So it exerts the friction this direction. That is the unbalanced force accelerates the car. Now when the car moves, the wheel Y also rotates in the same direction. If the wheel is rotating this direction, the wheel Y also rotates this direction. Why this wheel rotates in the same direction? Which force rotates the wheel that direction? Think about that. When the car slips, if the car moves to the right, this wheel Y will try to slip on the road, on the floor, but there is friction. So when you try to slip, the friction will oppose the possibility of slipping to this direction. So it will exert a force opposite direction, but it has the axle here. So if you keep a coin and give a force this way, hold it at the center and give a force this way, it will rotate this way. So this wheel is rotated by the ground where it has friction with the contact point. That force rotates the front wheel. Okay, so this is an explanation type question. Normally it comes in A-level papers. So there's a inflated balloon attached to a trolley, and initially it was kept at rest. But when the knob is released and air is allowed to move away from the balloon, or when the air is released from the balloon, the trolley accelerates, moves moves towards right from rest. So by using Newton's laws of motion, explain this observation. Okay, you should know that all the motion, all the movement is due to Newton's third law. For example, when you walk, what do? You push the ground backwards. When you push the ground backwards, according to Newton's third law, the ground pushes you forward, and your body will have an unbalanced force in forward direction. So according to Newton's second law, you will accelerate in forward direction from rest. That is, you call walking. Same way, a car, I already showed it in the free body force diagram. If it is a rear wheel driven car, the rear wheel rotates and pushes the ground back. So the ground pushes it forward due to grip, the friction. So the car will have unbalanced force in forward direction. So when there is an unbalanced force in forward direction, according to Newton's second law, F equal ma, the car will accelerate in forward direction and move from rest. Like that, even rocket motion, what happens? The rocket pushes the exhaust gas downwards at larger force. According to Newton's third law, the gas will push the rocket upwards with the same larger force. And if that force is greater than the total weight of the rocket, there will be an upward resultant force. So according to Newton's second law, the rocket will have upward resultant force, meaning according to second law, it will accelerate upward direction. Same way, all the motions are due to or could be explained by using Newton's third law. So this explanation also the same. So here you can say when the air is released from the inflated balloon, the air will be pushed out towards left by the balloon. So balloon has its own elastic property. So the balloon will try to come back to its initial position. So the balloon will shrink and push the air towards left. So when the balloon pushes the air towards left through the hole, the air will push the balloon to the right. According to Newton's third law, you have to tell the refer the law. According to Newton's third law, air pushed the balloon towards right. But the balloon is fixed or attached to the trolley. So the whole system will have an unbalanced force towards right. According to Newton's second law, F equal ma, the whole system will accelerate towards right from rest. Okay, so same answer. The explanation is the same whenever they ask about motion based on Newton's laws. The explanation, the answer is the same always. Anyway, I'll write this answer. But that will be the same for all type of questions related to Newton's laws in terms of explanations. Okay, so this also one of the old question. A child is crouching at rest on the ground. The child now jumps vertically upwards. So initially he was at rest, now he is jumping vertically upwards. With reference to the forces acting on the child, explain what he must do to jump upwards. Your answer should include the Newton's laws of motion. Okay, so we'll think about first the forces acting on it. What do you do when you jump? You push the ground, is it? By using your muscles, you push the ground harder downwards. So first we can see when he's at rest, what are the forces acting on him and how can we relate those forces? Then when he jumps, how these forces changes, we'll think about that. Okay, so we'll think about the forces acting on the child. So answer, I'll write it here. So if I think about the forces acting on the child, so when he is at rest, what are the forces acting on him? So I'll consider the force acting on the child and the ground. So what are the forces acting on it? First, his weight will act downwards. Earth is pulling him down. So weight is acting downwards. And he is on the ground. So he will push the ground downwards. Pushed by the child downwards. The force R I can call. The child is pushing the ground downwards. Ground will push the child upwards. We call it as normal reaction. So they should be on the same line of action. So I'll draw somewhere here the R. Yeah, the force R upward direction on the child. Okay, so when he is at rest, there are only two forces acting on it. The push by the ground R and the weight, they will balance each other. No resultant force. The child is at rest initially. Okay, so when he wants to jump vertically upwards, he can't change the weight. That only, that is constant because the mass is constant. Gravity is constant, G is constant. So that you can't change it. But what we do, he should push the ground harder. By using his muscles, he should push the ground harder. When he increases the R, initially R and mg are same. Okay, initially R and mg are same when he is at rest. But he should push the ground harder by using his muscles, and he should make R greater than mg by using his muscles. So when he pushed the ground harder, according to Newton's third law, the force acting on him or the force exerted by the ground on the child also will increase because they are Newton's third law pair of forces. So now this R also will become greater than mg. Now when you think about the child, there is a force upwards which is greater than mg. The downward force is the weight mg. So this force is greater than this one, means the child will have a resultant force upward direction. So he will accelerate upwards. That is called jump. He will move upwards. Okay, so that's the answer. You should say. So first you should refer the two forces acting on the child and what should we do to jump, how the force R is increased, then relevant Newton's laws you have to include when you are explaining. So again I am telling, initially when the child is at rest, the two forces acting on the child are weight and normal reaction. Third law pair of the normal reaction will act on the ground downwards. Let this force be R. We'll use R, easy to refer. When he wants to jump, the child should push the ground harder downwards and increase that force greater than his own weight. When that force increases, the ground, according to Newton's third law, the ground will exert same larger force on the child in upward direction. Now the child has larger upward force than his weight. There will be a resultant force in upward direction. According to Newton's second law, the child will accelerate up, and that is jump. Okay. Okay, so this question says that the diagram shows about the shelf which is behind the windscreen of car. So at constant velocity, the diagram says at constant velocity the pencil is at the rear edge of the shelf. But when the car is braking, the pencil moves to the front edge of the shelf. The question is the pencil has been left on the rear edge of the shelf, that is during the constant velocity, which is behind the windscreen, that is telling about the shelf of the car. When the car is braking, the pencil is against the front edge of the shelf. Explain this observation by using one of the Newton's laws of motion. Okay, so how to explain? We can say when the car is moving at constant velocity, the pencil is at the rear edge, so it also will move at the same velocity as the car, right? When the car brakes, okay, when the car brakes, the pencil won't experience any opposing force to slow down. Therefore, according to Newton's first law, the pencil will continue to move in the same direction. Why? The pencil has no further force to oppose its motion. So, according to Newton's first law, the pencil will continue to move at the same earlier velocity, which is greater than the velocity of the car, because car is slowing down now. So every moment, every second the car is slowing down, but the pencil has no opposing force to slow down its motion. So will continue its motion at the same velocity, which is greater than the velocity of the car. So the pencil will have every moment, it has a greater displacement than the car, or greater displacement than the shelf in the car. So the pencil has greater displacement, means it will catch up with, actually pencil is catching up with the front edge of the car. Pencil will catch up with the front edge of the car. So that's the answer we should write. Okay, so next we are going to analyze about what are the conditions for an object to be at rest or at equilibrium when it is under action of system of forces, more than one force. Okay, what's the difference between an object is at rest or object is at equilibrium? Okay, the first thing you should know, when object is at rest, it should not move. There should not be any change in its position, and it should not rotate. So when we say an object is at rest, we can say no motion, no rotation, or no spin about any point. When object is at equilibrium, the object can move. Object could move at constant velocity. Careful, I am not saying constant speed. Constant velocity means it could move on a straight line at constant speed. Straight line at constant speed. So they could move at constant velocity but no rotation. So constant velocity means no acceleration. No acceleration means according to F equal ma, a is 0, f must be 0. Okay, when we consider these two, the conditions to be at rest or to be at equilibrium is the same. There is nothing different. The condition for to be at rest or to be at equilibrium, first one, no resultant force. No resultant force. That means when you resolve all the forces acting on the object to any direction, along that direction, the resultant force must be 0. Say for example, there is an object, that object is at rest or equilibrium. The conditions are the same. Maybe it has a force, there is F1 acting at an angle theta 1. There is another force F2 that's acting at an angle theta 2, something like the theta 2. There is another force F3 that is acting at an angle theta 3. Like that, there are many forces acting on the object. But object is at rest or equilibrium, same condition. Now when you resolve all these forces into any direction, it's not necessary to consider horizontally or vertically. Any direction when you resolve all those forces, by depending on the angles you know, you can resolve it. In that direction or along that direction, the resultant force must be equal to 0. Okay, so when object is at rest or at equilibrium, when we resolve all the forces along any direction, along that direction, the resultant force must be equal to 0. So that is the first condition. The second condition, no moment or turning effect must be equal to 0. Total moment about any point must be equal to 0. So total moment, that means I can say total clockwise moment equal total anti-clockwise moment about any point. Careful, any point. The same thing I can say total clockwise moment must be equal to total anti-clockwise moment about any point. About any point. So the calculations based on conditions are related to these two conditions. Okay, so we are going to do questions related to this. So nothing else. When we resolve all the forces into any direction, the resultant force in that direction must be 0. When we take moment about any point, total moment 0, or I can say total clockwise moment equal to total anti-clockwise moment about any point. Okay, so these are the conditions. So, but we can analyze in terms of number of forces also, that I will do now before starting questions. Okay, so imagine an object is at rest or equilibrium under two forces. Say, how should they act? The two forces. Say, imagine there's an object. So it's at rest or equilibrium under two forces. How should they act? The two forces, they let them be F1, F2, right? So how should they act? So imagine if the force F1 is acting this direction, F2 is acting this direction, they are exactly opposite to each other. F1 equal F2, if I say F1 equal to F2, but they are acting in exactly opposite direction. Can it be at rest or equilibrium? No, it won't be at equilibrium or at rest. The reason, when even if the forces have the same magnitude acting in opposite direction, it's going to rotate. You can see that if you keep an object like this, something like a eraser, right? Keep an object something like this, and if you apply force this way on a table, you keep it on the table and apply forces in opposite direction, but they are not along the same line, what will happen? It will rotate, so it won't be at rest. The resultant force is 0. So F1 equal F2 means the resultant force Fr equal, they are acting in opposite direction, so that will be 0. Yes, resultant force is 0, but turning effect is there, so it won't be equal to, it won't be at rest or equilibrium. So the condition for an object to be at rest or equilibrium under two forces, first one, the two forces should act in opposite direction along the same line. They should act along the same line. So they should act along the same line this way. They should have the same magnitude. Okay, so then only the object will be at rest. Okay, so same way when we consider when object is at rest under three forces, object is at rest or equilibrium under three forces, there we can consider like this. The first condition, the three forces must be along the same plane. They should be co-planar forces. They must be along the same plane, the first condition. Then we can think about the three forces might be parallel to each other. That means parallel to each other. Something like, imagine you hang a rod. A rod is hung by using two strings. Maybe something, this is a rod. It has weight acting here, mg. There is a string attached to a roof or something like this. Here T1 tension is acting on the object, the rod. So there's the next string T2. So we draw the free body force diagram. Again, I'll draw it. The forces acting on it are, the weight is acting vertically down. The tension on this string is acting upwards. Let it be T1. This is T2. The string here, the tension is T1. Here the string T2. It's at rest. That means all these three are parallel forces because weight is acting vertically down. Tension on the string is attached vertically. This also attached vertically, T1 and T2. Okay. So here what is the condition? Here all these three forces are parallel. They will be on the same plane. They should be on the same plane, right? And the resultant of any two must act careful. Resultant of any two forces must act along the line of action of the third force in opposite direction. Say forget about this force now. I can find the resultant of T1 and T2. So resultant of T1 and T2 should be upwards. Forget about this force. Don't consider this now. So I can convert these three forces into two forces by considering the resultant of these two. So that is T1 plus T2. If I draw again that diagram, the T1 plus T2 should be somewhere. We'll see, imagine it's acting somewhere T1 plus T2. The weight is acting here. The weight is acting here. The T1 and T2, the magnitude of T1 plus T2 could be same as mg, but they are not acting along the same line. So what will happen? It will rotate. Same as what I drew earlier for two forces. Now I had converted three forces to two forces. So T1 plus T2 is the resultant of these two forces. It's acting upward direction. That T1 plus T2 might be can be same as mg in terms of numerical value, but if they act at some other point, then it will rotate. So the condition, what will happen? If it is at rest, if the system is at rest, then T1 plus T2 must act along the line of action of mg. So T1 plus T2 should act along this direction. Same way, forget about this force now. Forget about this force. So resultant of mg and T1, consider that one, mg and T1. So this is upwards, I know that, but I am not considering it down. So mg and T1, say imagine mg greater than T1 means the resultant will be mg minus T1. The T2 is acting here. So if I consider these two forces first, their resultant must be downwards, which is mg minus T1 should act here. mg minus T1 should act here exactly opposite to T2. Then only it will be at rest. So when an object is at rest or equilibrium under three parallel forces, the resultant of any two must be equal to the third force, and it should act along the same line of action of the third force, along the same line of action of the third force, but in opposite direction to the third force. Here you can say the resultant of these two must act along the same line of action of the third force, but in opposite direction to mg, and also T1 plus T2 must be equal to mg. Here mg minus T1 equal to T2. Like that we can show. Okay. Okay, so the object could be at rest or equilibrium under three non-parallel forces. How should they act, the three non-parallel forces? Imagine a picture is hung by using two strings or two chains, something like that. So the strings are attached along this line, so they are non-parallel. So the weight acting at the center of mass. Right, okay, so we'll draw the free body force diagram for this picture. Okay, so the picture, if I draw the free body force diagram, the weight will act along the same, along the center of mass. The tension T1 and T2 will act along these strings. How should they act? They all must meet at one point. The three non-parallel forces must meet at one point. So if I extend this line of action, so the line of action of mg is along this way. Line of action of T2 is along this way. Line of action of T3 is along this way. So you can see all these three line of actions are meeting at one point. they all must meet at one point. So when three non-parallel forces are at rest or equilibrium, they should be coplanar forces. They should be along the same plane, and they all must meet at one point. So if you push the picture a little bit to right, it will come back until the forces meet at one point. Otherwise, it won't be at rest. Okay, so when they meet at one point, here also, the resultant of any two must be equal to third force. So if I think about this point, the resultant of T1 and T2 should be equal to mg. Resultant of T2 and mg must be equal to T3. Resultant of T1 and mg should be equal to T2. And also I can say resultant of T1, T2 should be equal to mg. That should act along the same line of action of mg upward direction. If I forget about this mg, if I don't consider mg, T1, T2, so the resultant should be something like this. The resultant of T1 and T2, if I say Fr, so this is the mg. The resultant of T1 and T2 should act along this line, Fr. Same way, the resultant of T1 and mg should act along this line, opposite to T2. Resultant of mg and T2 should act along this way, opposite to T1, should have the same magnitude. Okay, so very important condition when object is at rest or equilibrium under three non-parallel forces, they all should be on the same plane and they must meet at one point. So if the object is at rest, what will happen? Resultant of any two must be equal to the third force and should act in opposite direction to the third force along the same line. Okay. Okay, so consider this diagram. There a rod, maybe we will take it for simplicity, it's like a uniform rod, is at rest by touching a horizontal rough floor and a vertical smooth wall. Okay, so then think about how many forces acting on it. Here, the number of forces acting on it is more than 3 forces. We'll think about it. So what are the forces acting on it? So the weight will act, because I said it's a uniform rod, we'll take the rod as uniform. So the weight will act at the center. The weight of the rod will act at the center. And there will be normal reaction from the floor. So let it be R1. There will be normal reaction from the floor, R1. The rod will try to slip and fall towards right. This end, this edge where it's touching the floor, that edge of the rod, the lower edge of the rod, will try to slip. You can see when you keep a rod something like it will try to slip like this. So the friction will act towards left. So the friction will act on the rod towards left. I'm showing these forces on the rod. The friction, Fr, friction will act towards left. It's a rough flow. But wall is a smooth, so there won't be any friction, but there will be normal reaction on the wall, this direction, let it be R2. So there are how many forces? 1, 2, 3, 4 forces acting. What's the condition? How should they act? The 4 forces. Will they meet at one point? I said 3 non-parallel forces should meet at one point. What about these 4 non-parallel forces? Okay, how to convert this? Now these two forces, Fr and R1, I can convert and find the resultant of Fr and R1. If I know the numerical values, I can find the resultant of Fr and R1. Okay, so if I think about the resultant of Fr and R1, I am drawing it again, the diagram. So the normal reaction from the wall will act this direction, R2. The weight of the rod will act from the center because it's a uniform rod, I told. So weight will act this way, mg. So the line of action of mg will pass. Line of action means, you know, they extend the line of force, any amount you can extend. So that's called line of action. So the weight will act vertically down, its line of action. And the normal reaction from the wall meet here. So the resultant of Fr and R1, if I find the resultant of Fr and R1, they are among them 90 degree. Imagine the Fr is this direction, Fr is this direction, the friction. The R1 is this direction, the resultant R, the normal reaction R1 is this direction. So the resultant of Fr and R1 should be this way. Should be this way. That's a resultant of Fr and R1. I'll draw it with green ink. Okay, I'll draw with green. So that is the resultant of this is the resultant of FR and R1. FR is acting left, FR is acting left. If I sketch a vector diagram, FR is acting left, the normal reaction from the flow is acting up. So the resultant of these two should act this way. But how should it act? The resultant of those two forces will act at this end. How should it act? It must pass through this point, because I have converted 4 forces into 3 forces, right? 3 forces. The third force is the resultant of R1 and FR. That resultant must pass through this line. So I can call that resultant as FR, put F capital R, I mark it here capital R. So that FR should pass through the point through which Mg and R2 are passing. Okay, so that's the way the 4 forces could be converted to 3 forces. Same way, 5 forces, if there are 5 forces also we can convert to 3 non-parallel forces. There also the final 3 non-parallel forces should pass through one point. Okay, so a picture of weight 30 Newton is hung by using 2 light strings. Find the tensions of them. So if I think about the forces acting on it, so they all 3 should meet at one point. I can say this is T2, this is T1. They meet at one point. The weight will act 30 Newton downwards. This is 40 Newton, 40 degree. This also 40 degree. Okay, so I told that when the system is at rest under 3 non-parallel forces, when we resolve any direction, the resultant force must be 0. So normally we resolve horizontally and vertically because those are the convenient directions. But if we resolve it to any direction, in that direction it should be 0. So I'll resolve it horizontally. So when I resolve horizontally, T2 cos 40 minus, you know the resolving, minus to the left, T1 cos 40 equal to 0. So when I take it to the right side, T2 cos 40 equal T1 cos 40. So cos 40 I don't need to find because they are going to get cancelled. So that means T1 equal T2. So remember that if the 2 forces are making it, when there are 3 non-parallel forces, but 2 forces make same angle, then they should have the same tension. So T2 equal T1, I can call it as T. Okay, now resolve it vertically upwards. So T sine 40 plus T sine 40 minus 30, that's a weight, equal to 0. So 2T sine 40 equal to 30. So T will be 30 over 2 sine 40. Solve it, you will get the tension. Both will have the same tension. That will be that will be 23.3 newtons. Okay, so this question picture that also the weight of the picture is 10 Newton. It's hung by using 2 light strings. One is in horizontal position, other one is making an angle 30 degree with horizontal. Find the tension of these strings. Okay, here, so the total moment must be equal to 0, but I am not using the principle of moments, that is total moment equals 0 or total clockwise moment equal to total anti-clockwise moment, that I am not using, because without using it I am able to find the unknown T1 and T2. Okay, but here since I am not using does not mean the moment not equal to 0. Students have wrong idea. They think questions related to moment normally in the exam papers comes separately. They have to use moment. But whenever questions comes like this, students never think about moment because they think we don't need to consider the moment. No, we need to consider the moment here also, but we don't need it because without using the principle of moment, I am able to find the unknown things, right? But here also the total moment equal to 0. Remember that. So here if I resolve vertically, so the forces acting on it are T1, T2 are the unknown force. This is the picture, the weight will act vertically downward. If I resolve vertically upward direction, T1 sine 30 minus mg equal to 0. But I know the mg is 10 Newton. So T1 sine 30 equal to mg. I take the mg to the right and substitute 10, so it will be 10 Newton. So T1 equal 10 over sine 30, that going to be 20 Newton. So the tension T1 is equal to 20 Newton. So then resolve horizontally, that also must be equal to 0. That is T2 minus T1 cos 30, T2 minus T1 cos 30. So when I resolve horizontally, the weight is acting vertically down. So that weight has no horizontal component. We learned that, I told that today. So the vertical vector has no horizontal component. So that won't come in this equation. So only the T1, T2 will involve. T2 minus T1 cos 30 equal to 0. But I know T1, that is 20. So T2 equal, substitute 20 and take it to the right. 20 cos 30, solve it, you will get the answer. That will be equal to 17.3 Newton. Okay, so here a box is kept on a rough inclined surface which makes an angle 40 degree with horizontal. Mass of the box is 5 kilogram. The question is, find the friction between the box or friction exerted by the inclined plane or inclined surface on the box and the normal reaction. Here also the total moment about any point must be equal to 0, but without using the principle of moment, I can solve it, right? Okay, so first we'll think about the forces acting on the box. Okay, when I think about the box, the forces, I'll draw the free body force diagram for the box. The box has weight downwards, so the weight will act vertically downwards. So the weight will act vertically downwards, mg. There will be a friction acting opposite. So the box has the tendency or intention of moving down, slipping down. So the friction will oppose the possible motion. It's not moving, but friction means the force that opposes the motion or opposes the intention of motion. So it has intention of slipping down. So the friction will act vertically upwards. I don't consider the dimension of the box. So imagine the box as a very tiny thing because we don't consider the dimension of the box, right? So what else acting? The normal reaction from the plane. So the normal reaction will act this way, perpendicular to the surface. The normal reaction will act this way, which is right angle to the surface. Normal means perpendicular to the contact surface. So that will act this direction. That is R. So I need to find R and F. FR and R. Those are the two things I need to find it. Okay, so here the angle is 40 degree. So this is 40 degree. So this is 40 degree. So if I extend this line and extend this line, okay, so normally I need to find the horizon. Normally students thinks the resultant force equal to 0 in any direction. So far we came across questions where we resolve all the forces horizontally and vertically. Here also, can I do that way? Should I resolve all the forces horizontally equal to 0, all the forces vertically equal to 0? Yes, you can do, nothing wrong. But mathematically, it might become little hard. Say for example, I'm not going to follow that method. I'm going to do some other method, but I'll show you what will happen. If I resolve all the forces horizontally and equal to 0, one by one we'll resolve it. Mg is already vertical, so that won't have any horizontal component. So that won't have any horizontal component. This one, Fr cos 40. Okay, then if I resolve this R, this is 40 with this line, this is 40, this is 90 degree, this is 90 degree. You can see this is 90 degree. This vertical, the weight, and this horizontal dotted line 90. So this is 40 means this will be 50. So this will be 40. Is it? This will be 40 degree. Can you see that? Because this is mg, vertical line. This is horizontal line. So this plane makes 40 degree because this is 40 degree. If I draw a horizontal line here, this will be 40. Parallel angles. So this is 40. But this vertical line and this is 90, the total angle. This is 40 means the force between the vertical line and the FR that is 50. This force will be 50. Again, this and normal reaction are perpendicular. So this is 50 means this is 40. Okay, so the normal reaction makes an angle 40 degree with the vertical line. Okay. So this will be 40 degree. This is R, the normal reaction. It makes an angle 40 degree here. Okay, so now I can resolve all the forces horizontally and vertically equal to 0. So Fr cos 40, mg has no horizontal component. If I resolve this one, so with the vertical line, R is making an angle 40 degrees. So R sin 40 minus R sin 40 equal to 0. Okay, so here solving it, you can get a relationship between Fr and R. So cos 40 sin 40, that means I can say Fr cos 40 equal R sin 40. So substitute the values of cos 40 and sin 40 and get a relationship between Fr and R. So that will be 0.766 Fr equal to sin 40, that will be 0.643 R. Right, so anyway, you can continue. So I can say R equal 0.766 over 0.643 Fr. R make the subject, bring it down, you can get it. But this is not the way we do this method, but I am just showing it. So 0.766 divided by 0.643, you will get it 1.19. So 1.19 Fr. So the normal reaction and Fr has the relationship, that is 1.19. Okay, now resolve vertically upwards. That means R cos 40. So if I resolve R cos 40 plus Fr sin 40 equal to or minus mg. So minus mg or equal to mg. I put minus mg equals 0. 0. So R I can put 1.19 Fr. Fr cos 40 plus here Fr sin 40 equal mg. Mass is 5 kilograms. So 5 into 9.81. Okay, so here we can solve, nothing hard, but lot of numbers are coming. I'll erase this part. Okay, so 1.19 cos 40, that is equal to 0.912 Fr. 1.19 cos 40 equals 0.912 Fr. Here again sin 40 Fr. So that will be 0.643 plus 0.643 Fr equal to 5 into 9.81. So that will be equal to 49.05. So solve this one. 0.643 plus 0.912, that will be 1.56 Fr equal to 49.05. Find the Fr. Divide 49.05 divide by 1.56, you will get 31.4. So the friction will be 31.4 Newton. Okay, so then R equal 1.19 Fr. So R will be equal to 1.19 Fr. You can use here Fr 31.4. So that will be 37.4. Right, so this nothing wrong. So, but we are unwantedly taking longer method. So the technique here is, you know, the two unknown forces, the normal reaction R and FR, among them 90 degree. Understand? So there are two unknown forces. Those are the friction FR and the normal reaction R. Among them, the red color line and the blue color line, among them, they are 90 degree. So the technique what I am going to use it means I am going to resolve all the forces first. I told any direction I can resolve. In that direction, along that direction, the resultant force must be zero if the object is at rest or equilibrium. So if I resolve all the forces along this line, along the FR, then R won't have any component in that direction. So I told that when you are resolving a vector through 90 degree, no component. The component will be zero. Horizontal vector has no vertical component. Vertical vector has no horizontal component. The same way that horizontal and vertical, among them 90. So when you resolve vector through 90 degree, it won't have any component. I'm going to use that technique. So if I resolve all the forces along FR, so I won't have any component of R along that direction. Only one unknown is FR. So I will be able to find the unknown force FR. So I am going to use that technique. This is actually nothing wrong, but unwantedly we are following a longer method. So I'll raise this answer. Okay, so we'll find the unknown angles here. So I need to resolve all the forces along FR. So R won't have any component in that direction because when you resolve a vector through 90 degree, no component. So along this direction when I resolve MG, I should resolve along this direction. So what is the angle? This one. How much will be this one, this angle? So you know that this is 40. So if this is 40, this is 40 because opposite angle. This line and this line when you consider this is 40 degree, so this is 40, but this line and this line among them perpendicular, this is horizontal, this is vertical 90 degree, this is 40 because opposite angle, so this will be 50 degree. Okay, the weight makes an angle 50 degree with the slope. So I'm going to resolve along this direction FR. R won't have any component because 90 degree when you resolve it, it won't have any component. So FR, I am taking this way, right? I am resolving along this way. I can put arrow like this way. I am resolving along this direction, that is with the 40 degree. So along this direction, FR. This one if I resolve it, mg cos 50 minus mg cos 50 equal to 0. So find the FR. FR is equal to mg cos 50. So that is mg is 5 into 9.81 cos 50. Solve it. You will get the answer. That will be equal to 31.5 Newton. Then we will resolve it along this direction. So now I am going to resolve it along R. When I resolve it perpendicular to the plane, along this way, if I resolve it, the friction won't have any component because that is perpendicular to R. When you resolve through 90 degree, it won't have any component. So if I resolve it along this direction, that means we normally draw this way. So I am going to resolve perpendicular to the plane, perpendicular to the slope, perpendicular, that is along the R I am resolving it. So when I resolve it this way, R minus, only thing I need to resolve the weight mj. So this is 40 degree because this is 90 degree. This is 50 means this is 40. R minus mg cos 40 equal to 0. So R equal mg cos 40, 5 into 9.81 cos 40. So you will get an answer which is 37.6 Newton. So normally what we say, when object is kept on an inclined plane, so we normally tell the students to remember that. Why? For this one, so rather than thinking about these angles, we normally say when object is kept on an inclined plane, the weight of the object will be have components along the plane and perpendicular to the plane. We normally tell the students to remember that. So the weight of the object will act vertically downwards. So remember this, the weight of the object will act vertically downwards. This is theta. the component of the weight along the plane down will be mg sine theta. Component of the weight along the plane downward will be mg sine theta. So how is it be mg sine theta? We'll draw a normal to this line also. This is 90 degree. So we'll extend this line also, the weight. So this is theta, this is 90 means this is 90 minus theta. If this is 90 minus theta, this also 90 minus theta because opposite angle. The red color line and the black color line among them 90. So this angle how much? This is theta, this is 90 minus theta, this is 90 minus theta. These two lines are making 90 degree. This is 90 minus theta means this will be 90 minus 90 minus theta. It will be theta. So this angle will be theta. Okay, so this makes an angle theta. So this theta means this also theta. So we resolve the mg along this direction. Mg cos theta. Mg cos theta through the angle cos. The component of the weight along this plane mg sine theta. Or I can say this is theta, this is 90 minus theta. This is perpendicular to this one, so this is theta. That way also we can say this is theta because this is 90. This line and this line among them 90. So this will be 90 minus this angle 90 minus theta. That will be theta. So this is theta. So resolve the weight perpendicular to the plane mg cos theta. I need to resolve it. Mg perpendicular to the plane means through the angle theta, mg cos theta, to get the component along the plane downwards, move it away from the angle mg sine theta. Okay, so the component of the weight along the plane down mg sine theta, component of the weight perpendicular to the plane will be mg cos theta. Better remember that. So the theta is the slope, the angle of the inclined plane with horizontal. Okay, remember the components along the plane down mg sine theta, perpendicular to the plane mg cos theta. Okay, so this question, a sphere of radius 5 centimeter and the weight of the sphere is 20 Newton is at rest touching a vertical smooth wall with a support by a light string of length 15 centimeter. The question is find the tension of the string and the normal reaction from the wall on the sphere. Okay, here also the condition what I said, the resultant force in any direction must be equal to 0. Also the total moment about any point must be 0. In this question also I don't need to use the principle of moment. Without using it I can solve it. Okay, so we'll think how many forces are acting on the sphere. A sphere of weight 20 Newton, so we should take the sphere as a uniform sphere. So nothing is mentioned, so we'll take it as a uniform sphere. The weight will act from the center. So the weight will act from the center. So the weight acts from the center like this way. So the normal reaction will be from the wall, smooth wall, so it will be perpendicular to the wall. So the string which is shown on the diagram is a rough diagram, it's not a picture, so it's a rough diagram shown on the string. So we know that the tension of the string should pass through the two forces R and mg meet at the center of the sphere because mg is acting from the center because it's a uniform sphere. The normal reaction will act from the wall, smooth wall, that will be perpendicular to the wall means, you know, for a circle if you draw a line perpendicular to the tangent, the wall is like a tangent to the circle, so that will pass through the center. So the tension of the string also should pass through the center. So this is actually a question from a book, it's a rough diagram, so it's not a picture, so we have to redraw it. So the tension will pass through the center because I told that when object is at rest under three non-parallel forces, all three must meet at one point. So these two forces meet at center means the third force, the tension, also must meet at that point. So I should redraw like this. Right, now the tension is acting this direction, right. So these are the three forces acting on it. I know the length of the string. Length of the string is 15 centimeter. The radius is 5 centimeter. So I can name this. This I name it as O, the center. This is P, this is A. So in the triangle AOP, this is 90 degree. So I need to find the angle theta. This angle I need to find theta. Okay, so if I find that theta, this also will be the theta because alternative angle, this also will be equal to theta. Okay, so that will be theta because alternative angle. Okay, how can I find this theta? In this triangle, the triangle AOP, sine theta equal to opposite AO over PO. AO is 5 centimeter, radius is 5 centimeter, so 5 over PO, P to O, how much should it be? P to the surface, the length of the string is attached to the surface of the sphere, so the length of the string from P to surface is 15 centimeter, from surface to center is 5 centimeter, so AO is equal to P to surface plus that point O, 15 plus 5, 20. So find the theta. So it's going to be 0.25. So find the theta. So theta will be equal to 14.5 degree. So I found the angle theta. Okay, so after finding it, now I can resolve all the forces vertically equal to 0, all the forces horizontally equal to 0. Here also, I don't need to use the principle of moment, but moment equal to 0. Okay, so I found the angle theta. So this angle also equal to theta. This vertical line makes here 14.5 degree. Find the tension of the string. So to find the tension of the string, we'll resolve it. We know the weight of it. Weight is given 20 Newton. So first part, I can resolve vertically up. So T cos theta, this angle is theta with the vertical line. This angle theta because this is theta, alternative angle. T cos theta minus mg equal to 0. So T cos theta is 14.5 equal mg 20. Find the T, that is 20 over cos 14.5. So that will be equal to 20.7 Newton. So I found the tension. To find the normal reaction, resolve horizontally, second part. R minus, if I resolve this, R minus T sine theta. Mg won't have any horizontal component because Mg is vertically downwards. So R minus T sine theta. T sine theta equals 0. So R equal T sine theta. So I know the T, I found it here 20.7. Sine theta, we know that. Anyway, sine theta I already found it, 4 over 20. So 1 over 4. 5 over 20 sine theta, 1 over 5 over 1 over 4. I can just substitute in. So sine theta, I can directly substitute because sine theta only I am finding it. 5 over 20 sine theta, 5 over 20, that is 1 over 4. So I don't need to substitute that. I can say into 1 over 4. So that will be equal to 5.17. Okay, so this question, a non-uniform rod PQ of length 1 meter, so P to Q 1 meter is hung by using 2 light strings. Center of mass of the rod is at a distance of 60 centimeter from the end P. So it's hung in a horizontal position. Okay, so here the rod which is non-uniform, its center of mass is at a distance of 60 centimeter from P. You need to find the tensions T1 and T2. So here also the total result, the resultant force in any direction equals 0, but there are only vertical forces. Here I need to use the principle of moment because there's no other way I can find the tensions T1 and T2. So for example, if I resolve all the forces into vertical direction, all are already in vertical direction. So that means T1 plus T2 minus mg, which is 20, equals 0. So T1 plus T2 equal 20. So there are two unknowns. But I have only one equation. Here I can't resolve them horizontally because this is vertical, this is vertical, this is vertical. No other way of resolving in any other direction. So what can I do? Mathematically, when there are two unknowns, I need two equations. So to get the next equation, I am going to use the principle of moments. So far in all the questions what I did earlier, conditions for equilibrium there, I did not use moments because I didn't need it, right? But here I have to use it. So we'll take moment about this point. So I'll take this point as a point, I'll call it as x. Take moment about x. If I take moment about x, you know that T1 is passing through x. That won't come in my equation. So this is 60 centimeter. This is 10 centimeter given on the diagram. So this will be 50 centimeters. So I'll take moment about x. You know, moment means force into perpendicular distance. So the weight is acting 20 downwards. The perpendicular distance of weight from x is, this is 60 minus 10, 50. So 20 into 50, which is clockwise direction. That is clockwise direction. About x, T1 won't be there because it's passing through the x. The perpendicular distance of T1 from x is 0 because it's passing through x. So that won't come in my equation because the perpendicular distance of T1 from x is 0. So this is clockwise moment. That must be equal to anti-clockwise moment T2 into this length. This is 1 meter. This is 10 centimeter means this will be 90 centimeters. So T2 into 90. I will find the T2 now. Then I can substitute here to find the T1. So T2 will be 11.1 Newton or 11.11 Newton. So T1 will be, use the equation 1. So T1 will be 20 minus T2 when you take it out. So 11.1. So that will be 8.9 Newton. Okay, so in this question also, I need to use moments. I'll show that because there's no other option other than moments. Principle of moments, I need to use it. So the uniform rod, so that means the weight will act at the center of it. A uniform rod, PQ of length 3 meter is at rest due to contact with a smooth vertical wall. So there will be only normal reaction. And a rough horizontal flow. The rod makes an angle of 30 degree with the flow. Weight of the rod is 20 Newton. Find the normal reaction exerted by the wall. So first we'll think about the free body force diagram. So the friction exerted, the normal reaction on the ground, let it be R1. It will pass like this, the line of action. The R2 will be here. It will go through like this. The weight will act at the center. So the weight will act at the center. So this is 3 meter means 1.5, 1.5. The weight will act vertically downwards, which is 20 Newton. Okay, so friction will act here because the rod will try to slip to the right. So the friction will oppose it. The friction will act towards left. Okay, so I have drawn all the forces acting on it. So okay, so it's simple actually. Looks very complicated, but actually it's simple actually. Okay, so first part, find the normal reaction exerted by the wall. This R2 they ask you to find it. This normal reaction R2 they ask you to find it. Okay, so find the R2. If I try to resolve horizontally, this has no horizontal component because this is a vertical force weight. R1 is vertically up. Only the horizontal forces are Fr and R2. So if I think about these forces, so there are only 4 forces, R2 a 20 Newton vertically down, Fr to the left, R1 vertically upwards. So they asked to find the R2, find the normal reaction exerted by the wall means R2 I need to find it. If I resolve horizontally, by considering all these forces, I will get R2 minus Fr because this is vertically up, that has no horizontal component. This also vertically down, it has no horizontal component. So R2 minus Fr equals 0, both are unknown. So what can I do? We'll take moment about Q. So if I take moment about Q, that advantage, Fr won't be in my equation, which is an unknown. R1 won't be in my equation because the perpendicular distance to Fr, friction from Q is 0. Because the force Fr is passing through Q, R1 also passing through Q. If I take a moment about a point through which unknown force is passing, careful. If I take a moment about a point through which an unknown force is passing through that point, the perpendicular distance is 0, so that force won't come in my equation. So I can avoid those unknown forces in my equation. So if I take moment about Q, the only 2 forces will be in my equation are 20 Newton and R2. Okay, so take moment about, so I'll write the answer, very simple answers, looks complicated. So first part, take moment about Q. Right. So one by one we'll take it. So R2, so the R2 about Q, look at it, the R2 is this direction. About Q, if I consider the moment, R2 will produce a clockwise moment. Think about this rod. The rod is like this. I'll raise it later. So R2 is acting this direction. R1 is acting vertically up, it won't come in my equation. Weight is acting from here downwards, 20 Newton. I'm going to take moment about Q, this is the point Q here. So if I take moment about Q, imagine if I keep the rod, this is the rod, imagine the rod is kept like this. I'm taking moment about Q, so hold it at Q. If I apply force R2 here, it will rotate in clockwise direction. So R2 will produce clockwise direction moment. The principle of moment says total clockwise moment equal to total anti-clockwise moment. So R2 will produce a clockwise moment. The weight will produce, keep it at Q, the weight will produce anti-clockwise moment. Is it? So R2 will produce clockwise moment, weight will produce anti-clockwise moment. So what's the moment of R2? R2, the line of action of R2 is along this way. Line of action of R2 is along this way. So I should consider the perpendicular distance from Q to line of action of R2. So the perpendicular distance from Q to this perpendicular distance is this one. This is the perpendicular distance I need to consider when I take moment of R2 from Q. Moment says force into perpendicular distance to the line of action of force. So this is the line of action of force. From Q, the perpendicular distance to this line of action of force is d1. How much is it? This length is 3 meters. This is 30 degree, means this is 30 degree. So how much d1? So if I consider sine 30 equal opposite, that is d1 over pq, the length 3 meters. So d1 will be 3 sine 30. Okay, the length, this one is 3 sine 30. Same way, for 20 Newton, what's the perpendicular distance? I need to consider, this is the line of action of 20 Newton. From Q, the perpendicular distance will be this one. This is the perpendicular distance. For this line of action, from Q, this is the perpendicular distance. So this is 30 degree. This length is 1.5 because it's a uniform rod, weight is acting at the center. So I need to find this length. How much is it be? 1.5 cos 30. 1.5 cos 30. Simple. So I'll get the moments, right? So I know everything now. Take moment about Q. So clockwise moment is R2 times 3, that is this length, 3 sine 30 equal to the weight 20 Newton will produce anti-clockwise moment. The distance to this weight from the NQ will be, this is 1.5, the length of the center of mass from Q is 1.5, 1.5 cos 30. So 20 into 1.5 cos 30. Solve it, you will get a very simple equation. So that will be 17.3 Newton. So R2 will be 17.3 Newton. Second part, find the normal reaction exerted by the flow. So normal reaction exerted by the flow, that is very simple. Resolve it vertically upwards. I don't need to take a moment. Resolve vertically upwards. Horizontal force, no vertical component. When FR, horizontal force, no vertical component. Only vertical forces are R1 and 20. So R1 minus 20 equals 0. So R1 equals 20. See, simple question. Then third one, find the friction between the flow and the rod. Also very simple. I don't need to take any moment. Resolve horizontally. So when I consider horizontally, only two forces are there. R2 minus FR equals 0. So R2 I found it only 17.3. So FR of, so 17.3 Newton. Very simple question. Okay, so this question, PQ is a uniform rod and its length is 2 meters and the weight is 10 Newton. At the NQ, it's carrying weight 20 Newton and it's kept in horizontal position due to support from a string, a light string, which makes an angle 30 degree with the rod. The rod PQ is nailed at P. It's pivoted at P, means it can rotate about P. There's a nail, so there will be a reaction force. That's a question. Third part. First part, find the vertical component of the tension of the string. Okay, so there I need to consider again here, I need to consider the moments, principle of moments, because I don't know what is the force acting at P. So what are the forces acting at P? I don't know. So I can draw a free body force diagram first, then I'll answer it. So draw a free body force diagram for this rod. So the weight is acting here, 20 Newton. The weight of the rod is acting at the center, which is 2 meter length at a distance of 1 meter. That will be 10 Newton. So at P, there will be force. I don't know what is the direction of force. I'll just take a force at an angle this way because there's a nail. There will be force. But I can't say whether it's going to be horizontal or vertical. Just I will say that force which is unknown as F. So rather than taking it as F, which is unknown, I can consider its component. So I can consider the horizontal component of that force as Fh, that has a force at an angle. So it should have a horizontal and vertical components. So that I'll take horizontal component FH, H stands for horizontal, vertical component FV. So if the vertical component is downwards, when I solve and find the FV, I'll get a negative answer. Right? I'll just take the horizontal component towards right FH. If it is actually towards left, I will get a negative answer for that. Okay, so there is a force at P. I don't know the direction, but it will have certainly a horizontal and vertical components. I took them FH and FV. Right. So there is a tension. The tension is acting along this direction. Tension is acting along this direction T, that makes an angle 30 degree. So that tension also will have a vertical component. That's the first part. Okay, so I'll consider the vertical component of the tension this way, TV. So I don't need to find the TV because first part they ask me to find the vertical component of the tension. Right, so first part, I take moment about P. The advantage, when I take moment about P, if H won't come in my equation because it's passing through P, So the perpendicular distance to FH is 0. So I told that if we take a moment about, the technique is if I take moment about a point through which unknown forces are passing, I can reduce those forces in my equation. So when I take moment about P, FH won't be in my equation, FV won't be in my equation. This tension also I'm going to resolve horizontally and vertically. This is the actual force acting this way. So I'm going to resolve these forces horizontally and vertically. So the vertical component I'll call it TV, and the horizontal component I will make it TH, which is horizontal component of the tension. Okay, actually the tension is acting this way. So here when I take moment about P, the TH won't be in my equation because TH is going to pass through the NP. You can see it's horizontal. We don't consider the thickness of the rod. So the TH is horizontal, that's passing through the P. So you can't find a perpendicular distance to TH from P. Say for example, you are taking moment about this point. There's a force acting towards this line, something like F. So if you take moment about this point, this force is passing through it. So you have no perpendicular distance. But if you take a moment about this point, yes, the perpendicular distance to line of action is this one. That's a perpendicular distance to line of action, right? But here I am taking moment about this point through which the force is passing. So no perpendicular distance. So in my equation, TH also won't be there. So here I am going to take moment about P. Okay, so when I take moment about P, the advantage, the unknown forces FV, FH, TH won't be there. So only there are three forces, 1, 10 Newton, 20 Newton, TV. Okay, so 10 Newton will provide clockwise moment. So that will be 10 into, the distance is 5, plus 20, that also will provide clockwise, 20 into, this length is 2, the length of the rod is 2. So this is 10 into 1, sorry, 10 into 1, the length is 1 meter. The length of the rod is 2 meter. So this is from here to the center of mass, we will call it G, the center of gravity, that is 1 meter. So 10 into 1, the weight of the rod is 10. Yeah, this is 20 into 2 equal to anti-clockwise movement only by vertical component TV into 2. So find the TV, that's all. So that will be 10 plus 40, 50 Newton divided by 2. So it's going to be 25 Newton. That's the vertical component of the tension, 25 Newton. Second part, hence find the tension of the string. So that is, I know that. What is TV? That is T sine 30. Is it? Tension is T sine 30 is equal to 25. So find the T. So that will be 50 Newton. Okay. Then third part, find the contact force at P. So I'll raise this part. We are finishing now that question. So okay, so third part. So these are the only forces acting on it. To find the horizontal component of the tension. So because I know horizontally, when I consider, if I consider horizontal direction, FH equal to T cos 30. So that's going to be 50 cos 30 so that will be 43.3 Newton. So vertically, when I consider in vertical direction, I have FV minus 10 minus 20 plus TV, I found it, TV 25 equals 0. So FV will be, so that will be minus 30 plus 20 minus 5, so 5 Newton. So what's actually the value of resultant force here? So horizontally 43.3, vertically 5 Newton. So F is equal to square root of FH squared, horizontal component of the force here, plus vertical component squared. Pythagoras theorem I can use because FV and FH are perpendicular among them. So that will be Fh squared is 43.3 squared plus 5 squared. Yeah, 43.6 Newton. Okay, so far we did questions related to conditions for equilibrium. But if the object is not at equilibrium, what will happen? There will be unbalanced force and the object will accelerate. So then we can use Newton's second law, right? So here the question is, there's an object of mass 2 kilograms is kept on a weighing scale, and the weighing scale is kept on the flow of a lift. So lift is accelerating or decelerating upwards or downwards. We need to find the reading of the weighing scale. So during the start of this lesson I said the weighing scale always reads the pushed by the object. So if I think about the push by the object means third law pair of the normal reaction on the object. Is it third law pair of the normal reaction? So answer I can consider like this. If I draw the free body force diagram of the object, it has weight downwards. The weighing scale, it will push the weighing scale downwards. When it is kept on the weighing scale, it will push the weighing scale downwards. It's a force R. So weighing scale will push it upwards with the third law pair R. Okay, so if the lift is accelerating, the object also should accelerate. Otherwise, the object will break the lift and come out, right? So it has to be, when you are traveling in a car, when the car accelerates, your body also should accelerate at the same value. So first part, uh, moves at constant velocity. So if the lift is moving at constant velocity, then there is no acceleration. So first part, I can use vertically upwards F equal ma for the object. So the force acting on the objects are 2r minus mg. The mass of the object is 2 times no acceleration because it's moving at constant velocity. So r will be equal to mg, that is 2 into 9.81, that is 19.62 Newton. So the reading will be the same because it reads the r. Right, second part, accelerates upwards at 1.2 meter per second square. So if the lift accelerates upwards at 1.2 meter per second square, the object also should accelerate upwards at 1.2 meter per second square. So Rf equal ma upwards I am using for the object. So R minus mg equal ma, because resultant force should be up because it's accelerating up means resultant force up means R must be greater than mg. Then only it can accelerate. The object also can accelerate upwards. So R minus 2 into 9.81 equal 2 into the acceleration is 1.2. Solve it for R. 22.02, I can say 22 Newton. So reading also 22 Newton. So when it accelerates up, the reading will become more than the weight. Remember that when something accelerates, when you keep an object inside a scale, keep an object on a scale inside a lift, and if the lift accelerates upwards, the reading will be more than the weight. Third part, decelerates upwards at 0.8 meter per second squared. So you know, when I consider upward direction, it's decelerating. So decelerating in upward direction means acceleration downwards, or deceleration upwards means acceleration is upwards negative. So use F equal ma upward direction, R minus mg equal ma, R minus 2 into 9.81 equal 2 into the deceleration is 0.8, so minus 0.8. Find the R. that will be 18.02. I can say 18 Newton. Fourth part, accelerates downwards at 1 meter per second squared. Accelerates down at 1 meter per second squared. So F equal ma, I am going to use downward direction. So accelerates down means resultant force should be down. So mg minus r, because mg should be larger than r if it is accelerating downwards. Mg minus r equal ma. So that is 2 into 9.81 minus r equal 2 into 1. Find the r. So r means that is the reading. R is the reading. So third law pair of this one, that's the r. That will be the reading. .62. Okay, so this question also something related to where the object is not at rest or not at equilibrium. So there's a resultant force acting. So I need to find the answers by using Newton's second law. So object is thrown on a rough inclined plane which makes an angle 35 degree at an initial velocity of 12 meter per second. Mass of the object is 1.5 kilogram. So I already told that you can better to remember the component of the weight if I think about the object. So the answer. So the object is, the box is kept at an angle on the inclined plane, is thrown at 12 meter per second. The component of the weight along the plane, I told that mg sine theta, mg sine theta, theta means 35 degree. Also, there is a force acting on the object which is friction 4 Newton that will oppose the motion, that also will act downwards, Fr, that also acting downward direction. Okay, so the motion is upward. It was thrown at 12 meter per second upwards. These two forces are acting opposite the direction of motion. So to find the deceleration, I am going to use upward direction, F equal ma, along the plane up, F equal ma. So these two forces are along the plane down, mg sine 35, that is downwards. I am using upwards because motion is up, minus 4 equal to ma. So minus mass of the object is 1.5 into 9.81 sine 35 minus 4 equal mass is 1.5 a. You will get a negative answer. So along the direction of motion a is negative means it is deceleration. So that will be minus 8.29 meter per second squared upward direction. So deceleration along the plane up. Okay, so second part, find the maximum distance moved along the plane upwards. So I can use equations of motion because it's a straight line motion, constant deceleration. So along the plane up, I can say v squared equal u squared plus 2as. It's going to decelerate along the plane up. The final velocity will be 0. The initial velocity is 12 meter per second. So 12 squared plus 2 into acceleration along the plane up is minus 8.29 into the distance moved along the plane, let it be d. Find the d. So that is 12 squared divided by 2 into 8.29. So 8.70 meters. Third part, they asked to find the time taken to reach the highest point. I can use V equal U plus AT along the plane up. So V is 0, U is 12 plus the acceleration along the plane up is 8.29 T. Find the T. 1.45 seconds. Okay, so this question also something related to Newton's second law. A trolley is kept on a table. Nothing is mentioned about the friction, so we can assume all the frictions are negligible. It's attached to a mass P, which is 1.2 kilogram over a smooth pulley. The system was initially kept at rest and then released. Mass P is 1.2 kilogram. Mass of the trolley is 1 kilogram. First part, find the acceleration of the trolley and the tension of the string. Okay, so we'll think about free body force.